Okay, so this P7 video is for gas laws and the graphs and calculations we can look at with them. There's going to be a separate video on the molecular model and kinetic theory which basically explains the reasons behind the laws. So one really important thing we need to realise when we're using gas laws is to make sure we use the absolute temperature scale, or the Kelvin temperature scale. And this is basically originally defined by using the gas laws, but its sort of modern interpretation is that at absolute zero, then a gas would have basically no useful thermal energy. Okay, so you can't extract any more energy from the gas when it's absolute zero. Effectively, it's minimum. And to convert from a temperature in Celsius to a temperature in Kelvin, all we need to do is add 273 onto the Celsius temperature. And to go the other way, obviously, we just need to take our temperature in Kelvin and subtract 273 to get a temperature in Celsius. So that means that a Kelvin temperature is always going to be a higher number than the corresponding Celsius temperature. Useful to remember. And again, the reason we're doing this is because if we don't do it, then none of our gas law equations will work. So you have to use Kelvin temperature scale, the absolute temperature scale, when we are using the gas laws. Okay, so let's look at the laws themselves. The basic idea behind them is that we have two quantities that we can measure about the gas that are fixed, and two that we allow to vary. And the four quantities are pressure and volume, temperature and amount of gas. Amount of gas is going to be constant in all of these, so we're not going to have situations in which the gas is going to be leaking out of the container or being put into the container. And then we fix one of the other three each time as well. In this case, for Boyle's law, it's temperature that's fixed, and allow the other two to vary. So pressure and volume can vary in Boyle's law. And so we've now got volume and pressure on the axes on our graph here. Pressure in kilopascals, so thousands of pascals, and volume in meters cubed. Okay, so what Boyle's law says is that for a fixed amount of gas at constant temperature, the pressure is inversely proportional to the volume. And what that means is that if we double the pressure, we will halve the volume. That makes sense because we know that if we put a gas under more pressure, it's going to be compressed and the volume will decrease. Mathematically, then, we have the equation pressure times volume equals a constant, so a fixed number. And again, that makes sense, because if I take a pressure and a volume to give me some constant, and I then double the pressure, to keep the right-hand side constant, I would have to halve the volume. So that mathematical equation encapsulates the words in the law. What does that look like on our graph? Well, it gives us this curve. Now, you might be required to actually plot the graph for this, given some data, or possibly to plot the graph given 1 point. So that's how we would do. Look at how we would do that. Let's say, for example, we were given the point a volume of 4 meters cubed and a pressure of 5,000 or 5 kilopascals. When we put those into the equation, that gives us a constant of 20,000. All you would need to do to plot the rest of that curve would be to find other pairs of pressure and volume that give you 20,000. The easiest way to do that is to take the one of the values and start halving it and double the other one. So given the axes we've been provided with here, we're all at the top of the volume axis, so it would make sense to halve that. If we halve the volume to 2, we would need to double the pressure to 10,000 to get back to our 20,000 constant, and there's that point. We could keep going. We halve the volume again to 1, double the pressure to 20,000, halve the volume to 0.5, double the pressure to 40,000. All of those pairs of pressures and volumes give us the same constant. That's what defines that curve on the graph. Okay. So if you were asked to do that, you could use that technique. You could also be given data in a table and asked to fill that in. And the same thing, they'd have to give you one row that was the pressure and volume both filled in so you could work out the constant. And then you would just have to make sure that the other rows multiplied together to give you the same constant. Other things you might be able to be asked to do, but less likely, is to sketch the pressure volume variation for a gas in a different situation. So this yellow curve is for one particular temperature and one particular amount of gas. If we were to double the temperature or the amount of gas, we'd get this dotted blue line here, which is the same shape but higher up the graph. Kind of makes sense. If we have more gas, the volume is going to be larger, okay, at all points. And similarly, that would give us a different constant. Okay, it gives us a different constant than the yellow curve. But if we moved anywhere on that dotted blue line, we'd get this same 40,000 constant now, different from our yellow curve, but constant on the blue dotted line. And if we use a second blue dotted line to show what it would look like if we had half the amount of gas or half the temperature, again, a different constant, this time 10,000. So you could sketch at least the graphs for different higher or lower temperature situations if you were given one that you knew. How do we use it in a calculation? Well, Boyle's law calculations, unlike the graph, are a little bit simpler because there are no temperatures to convert. So we don't need to worry about our absolute temperature scale because the temperature is constant. So let's have a look at this example. A car tyre at a pressure of 28 psi, or pounds per square inch, has a volume of 0.03. It's up on some jacks and we lower it down so that the tyre pressure is then increased as it touches the ground to 32 psi. And assuming the temperature remains constant, what would be the volume of the air in the tyre now? So before we do any of these calculations, it's useful to try and work out which direction the numbers are going to move in. If we increase the pressure, we know the volume should decrease, so we're expecting a smaller number than 0.03 for our answer. You might be a bit worried about the psi, the units of pressure, but actually, although we have to be very careful with our temperature units for these calculations and make sure they're in Kelvin, we don't need to worry about the pressure and volume units, provided they are the same in our starting and final situation, which they are here. Okay? So what do we do in these problems? Well, what we do is in step 1, right, we use the known situation to work out our constant. So we know the pressure is 28 psi, and the volume is 0.03, multiply those together to get our constant. And then we use that same constant in the second situation, where we've increased the pressure, to work out what the volume would be. So same equation written down again, put the constant in from the previous part and the 32 in from the second situation in the question, and rearrange it by dividing both sides by 32 to get our volume of 0.0263. 3 significant figures there. Don't write down all the answers on your calculator, all the digits on your calculator, because it gives us an unnecessarily large number of digits to write down, and also gives us a false impression of the precision that we've got in our answer. Okay, and once again, remember, units don't matter for the pressure or volume as long as they are consistent, so that's fine. And it's done what we expected. We've decreased the volume of the tyre from 0.03 down to 0.0263. Okay, next law, Charles's law. Graph for this is a bit more straightforward. This time we're fixing pressure and amount of gas rather than temperature and amount of gas, and we are now allowing temperature and volume to vary. Okay, and as you probably already know, if you heat a gas up, it should expand. Then it suggests that if we increase the temperature, we increase the volume, and indeed what Charles's law says is that the volume is directly proportional to the absolute temperature. So if we double the absolute temperature, we will double the volume. And that's encapsulated in this mathematical relationship, the volume divided by the temperature is a constant. Again, this makes sense because that's basically a fraction, and we know that if we double the number on top of a fraction and double the number on the bottom of the fraction, then the fraction remains essentially unchanged, so it is constant. So that makes sense. And on the graph, that is a nice straight line. So this is easy to do on the graph. If you have even a single point on the graph, then all you need to do is to draw a line that goes through that point and through 0, 0, and you will have the correct line for your relationship. Much easier than the curved one. Again, we can demonstrate that the law works by picking some points on the graph. So a volume of 3 and a temperature of 500 here gives us a constant of 0.006 when we did a division. And any other point we pick will give us the same constant. Once again, we can draw other lines to represent Charles's law, the variation of temperature with volume at different fixed pressures or fixed amounts of gas. So this line up here would actually correspond to half the pressure because the volume got larger, or double the amount of gas, which would obviously double the volume as well. And the line down here would correspond to double the pressure because the volume's got smaller, or half the amount of gas. And you can see again they give us different constants from our yellow line. But those values would be constant anywhere on those dotted blue lines. Okay, so using Charles' law in a calculation, a little bit trickier because we've got to remember the temperature conversions, because now temperature is one of our variables. So here's an example. A sealed balloon at 27 degrees C has a volume of 400 centimeters cubed, heated and expands to a volume of 440 centimeters cubed. What is the new temperature? They haven't been told here that pressure is constant, but we're not getting given any information about it, so you can safely assume that it's Charles's law we're using. So just a general piece of advice when you're selecting the equation, whichever quantity you're not given information about, you need to use the equation that is missing that quantity. So there's no mention about pressure here, and certainly no mention about pressure changing, so we're okay to use volume divided by temperature as constant. So first thing to do now is to convert our temperatures to Kelvin if they're not already in Kelvin. Do watch out, you might get one that's already in Kelvin. You don't obviously need to convert it again if you've got that. But this is in degrees C, so we need to add 273 to get 300 Kelvin. Nice round number. And then it's the same as before. We just use the known situation with the converted temperature to get our constant. So our starting volume is 400 and our starting temperature is 300, so that gives us a constant of 1.3 recurring. Try and keep all the digits in your constant in your calculator to avoid rounding errors, and only round off at the end of the question. That's generally good advice. Step 2, again, we just use the new volume and the constant we worked out in part 1 to work out the new temperature. If you're not happy with rearranging things, especially when the quantity we're after is on the bottom of the division, you can use the little triangle method. So the 440 goes in the top because it's on the top of the division here, and temperature in the bottom because it's the bottom of the division, and then the constant in the remaining space. Cover up the temperature, and that tells us that what we need to do is 440 divided by 1.33 to give us 330 Kelvin for the temperature. And obviously the last step, because it asked us to do that, is to convert the temperature back into degrees centigrade, and to do that we subtract 273 from the 330 to give us 57 degrees centigrade. And again, just check it makes sense. The question tells us that we've heated the gas up, and indeed the temperature has risen from 27 to 57, so that makes sense. Okay. The final law that we need to look at will be the pressure law, but just again, another note about the units here. You might be worried that the centimetres cubed are not standard volume units, but again, they're the same volume units for the start and the end, so we do not need to convert. Okay, so finally then, pressure law. This time, the one remaining thing we haven't kept fixed is the volume, and we're allowing the temperature and pressure to vary. And again, what happens here is we get a directly proportional relationship. That if I double the temperature, absolute temperature, I double the pressure. This kind of makes sense because a higher temperature gives us faster movement of molecules, which means that they'll strike the walls of the container more often and harder, and that increases the pressure. More detail on that in the other video about the way that the gas laws work. Okay, so that gives us a very similar mathematical relationship to the previous law, but this time it's pressure divided by temperature as a constant. And again, it gives us a straight line, not surprising. And we can do the same trick by reading off the values from the graph to show that we have a constant. And again, the same thing, we can draw a different straight line that would correspond to a different amount of gas. This time, if you had half the volume, that would mean more pressure because you pack the same amount of gas into half the volume, or you pack double the amount of gas into the same volume, so that's going to increase the pressure. And the other line would be double the volume, so you let the gas particles be further apart, they're striking the walls of the container less often, so less pressure, or half the amount of gas, again, striking the walls of the container less often, so less pressure. So we can draw those other straight lines on there as well. A calculation here then, this is a slightly more complicated one. I've kind of thrown the tricks that you might see into this one. Again, we write the equation down. And this time I'm going to use a starting and end situation that involves a temperature change. So we've got a sealed 170 litre oxygen cylinder heated in a warehouse fire from 17 degrees C and a pressure of 137 bar. A bar is just a pressure equivalent to 1 atmosphere, to a temperature of 1200 degrees C. Will the cylinder fail if it's rated for a maximum pressure of 400 bar? So what we're really being asked to find here is what is the pressure of the cylinder when we increase the temperature, and is it over 400? So that's a slight twist to what we've been done before. We're not just calculating a straight value, we have to calculate and compare. The other tricky bit is we've got two temperatures and we need to convert them both. We have a starting temperature and an end temperature, and again, step 0, we do that first, add 273 to both of them to get 290 Kelvin for our starting temperature and 1473 for our final temperature. And then it's basically the same. We use our known situation at the start, our temperature, converted temperature of 290 Kelvin and our pressure of 137 bar to find our constant. 137 divided by 290 gives us this number. And then we use that constant plus the new temperature substituted into the equation to give us our pressure. We want to know what the pressure is, so we multiply both sides by the 1473 so that we get an answer of 696 bar. Okay? And that clearly is more than the 400 bar in the question, so the tank will fail. Now you'll notice that there's one number we haven't used here, which is actually a volume, 170 litres, and the reason is that they've just told us what this constant volume is. Okay, so you might be, if you were presented with this and you weren't told that it was the pressure law you needed to use, it might be a bit confusing because you've got more information. So what you need to do is to look at the thing that's changed in the question, which is the temperature. So you have to use one of the laws that's got temperature in, so it can't be Boyle's law, right? And then you have to look at the thing you've been asked for, which is the pressure. So you have to use the law that's got pressure and temperature in. So that's the way you pick which one to use. Okay, that's the pressure law calculations. The next video will deal with the molecular model and kinetic theory of how the pressure laws basically work and how we might experimentally check that they are correct.